Hi all. Today we discuss Fourier series. This is the last topic of our syllabus. First we start with the definition 8.9. A trigonometric polynomial is a finite sum of the form f of x equal to a naught plus sigma n equal to 1 to capital N a n cos n x plus b n sin n x where x is real. And this a naught, a1, a2, etc., b1, b2, etc. are complex numbers. So these are the complex numbers, and this f of x is called, the right hand side of f of x is called a trigonometric polynomial. So by means of the identity, we have discussed the e of I x equal to c of x plus I times s of x, or equivalently you can write this as e power ix equal to cos x plus I sin x. You can write this f of x as the trigonometric polynomial takes this form: f of x equal to summation minus n to n cn e power I n x. Okay, so this is the most convenient form of this trigonometric polynomial. In later we will use this form of the trigonometric polynomial to define some finite sums and trigonometric series. This is due to the replacement of this cos nx by e raised to I nx plus e power minus I nx divided by 2, and sin nx is e raised to I nx minus e raised to minus I nx by 2i. When you replace these two quantities in this equation, in the expression of f of x, you can easily get an expression for f of x in this manner. So please try it as an exercise. So I left to you to do this derivation. So try to express f of x is equal to summation minus n to n. So this summation is, in fact, the small n varies from minus n to capital N, minus capital N to plus capital N. So please use these formulas to get this expression. Okay, so I left it as an exercise. And now we use this f of x, or from this expression of this f of x we can extract the coefficients of this trigonometric polynomial using the fact that this e raised to I nx has the period 2 pi. Therefore we write this if this n is a non-zero integer, n is a non-zero integer, we have e raised to I nx. Okay, this is the derivative of e raised to I nx by in. Okay, is the derivative of e power I nx by in. When you differentiate this expression, you will get e raised to I nx itself. Okay, and this has also the period 2 pi. So we evaluate the integral. Then we evaluate the integral 1 by 2 pi minus pi to pi e power I nx dx. Okay, we know that the integral of this is e raised to I nx by n, because this is the derivative of that. So we write this as by integrating we can get this is 1 by 2 pi e power I nx by in from minus pi to pi. Since these functions have the this function has the period 2 pi, you can get this value as 0 if n is equal to n is not equal to 0, and because if n is not equal to 0, then this e raised to inx has the period 2 pi, then this quantity in this bracket attains the same value at minus pi and pi, so you will get the value 0 for n not equal to 0. For all other n, so the only possibility is of getting a non-zero value is at n is equal to 0. Okay, at n equal to 0, this expression becomes 1 by 2 pi minus pi to pi. This becomes this 1 dx. Okay, if n is equal to 0, this integrand becomes 1. So this will be 1 by 2 pi I times x from minus pi to pi. So that will give 2 pi upon 2 pi, that will be 1. So if n is equal to plus or minus 1 plus or minus 2, that means n is not equal to 0, we can get the sorry, n is equal to 0, we have this value n equal to 0, this value, and when n is equal to non-zero value, that means n is equal to plus or minus 1 plus or minus 2 etc., we have the value 0. Okay, so now we write this integral minus pi to pi e power I n x dx will be 0 if n not equal to or 0 or n equal to plus or minus 1 plus or minus 2 etc., and 1 if n is equal to 0. Okay, using this fact you can easily evaluate these coefficients of this trigonometric polynomial. Okay, that is using the idea this integral 1 by 2 pi minus pi to pi f of x e power minus I m x. Okay, when you integrate this, you can write this as 1 by 2 pi minus pi to pi. Our f of x is summation minus n to n. This is c n x c n times e power I n x, c n times e power I n x into e power minus I m x dx. Okay, so this will become 1 by 2 pi or minus pi to pi. This can be written as summation minus n to n cn e power I times n minus m x dx. Okay, so since the integrand contains only finite number of terms in this summation, you can interchange the summation and integration as well. So you write this summation minus n to n 1 by 2 pi integral minus pi to pi cn e power I n minus m x dx. Okay, so in this case we have already proved that this integral vanishes when n not equal to m. Okay, so only the non-zero value for this integrand will be obtained if n is equal to m. Okay, so that means at when n is equal, so this summation, when you expand the summation, the only surviving term corresponds to n is equal to m. Okay, so at that case we write it contains only one term, that is 1 by 2 pi minus pi to pi cm e power, at n equal to m we have this quantity is 0, so e power 0x I0x dx. Okay, so this will be cm times 1 by 2 pi minus pi to pi 1 dx, but this value is 1, so this will give cm. So this is the way we extract the coefficients of f of x. We start with this integral, so you can get this cm is equal to this one. So where f of x equal to summation minus n to n cn e power I n x, then cm, each coefficient can be obtained using this integral 1 by 2 pi minus pi to pi f of x e power minus I m x, okay, dx. So we use the conjugate of this if we use the conjugate of e raised to in x to obtain the or extract the coefficients of this trigonometric polynomial. Okay, so therefore if you evaluate this expression for all the values of m, we can get this this m this if mod m is greater than this capital N, then there is no this e raised to inx. Okay, so there is no there will not be the presence of e power inx. So in this case, we have all the cm's or the right hand side. This integral will be 0. So all those cm we have 0. Okay, and the cm will be non-zero only if this mod m is less than or equal to capital N. Okay, so this cm exists as the coefficients of f of x. Okay, so now on these discussions we can get some remarks on this. With use of whenever the cn conjugate, this cn conjugate is equal to c minus n, then you can get that polynomial as a real trigonometric polynomial. So in this case, this is if and only if the f of x equal to summation minus n to n cn e power minus inx will be real. Okay, so this is one of the interesting observations for this, and we use these discussion to define a trigonometric series, okay, rather than trigonometric polynomial. So we write this is minus infinity to infinity cn e power inx. So this is what we called a trigonometric series. So this is the definition of trigonometric series, and the corresponding trigonometric polynomial what we have discussed earlier is going to be the partial sum of this is the partial sum of this trigonometric series. So using the convergence of this sequence of partial sums, we can get the convergence of this trigonometric series as well. Now we have the definition of Fourier series. Okay, so the above discussions lead us to define this Fourier series. So to define Fourier series, we start with an f, which is an integrable function. If f is an integrable function on minus pi to pi. Okay. For the time being, we are defining the Fourier series on the interval minus pi to pi. Then, if we start with an integrable function f from this interval, then we define the numbers cm defined by the equation cm is equal to integral 1 by 2 pi minus 1 by 2 pi integral minus pi to pi f of x e power minus I mx dx. Okay, suppose we define cm in this manner for all integer m. Okay, so first of all we start with an integrable function, and we define immediately the coefficients cm for all integers. We we are not aware of the expression of this f. This f need not be a trigonometric polynomial. So this can be any integrable function on minus pi to pi. So start with this integrable function. We define the coefficients using this integral. Okay, since this is integrable, then f of x in the power I mx minus I mx is also integrable. Then this cm's are defined for all integers and need not be there is no restriction for capital N or something. So because this f need not be a trigonometric polynomial, so this is an arbitrary function. So using this integrable arbitrary integrable function, you define this coefficients for all n. Okay, so these are called the numbers or the coefficients are called Fourier coefficients. Are called Fourier coefficients of f, and using these Fourier coefficients we define a series summation minus infinity to infinity cn e power inx. Okay, this is called, define this is called Fourier series, called the Fourier series of f. Okay, so this is the definition of Fourier series. So we start, if you can we can define Fourier series for any integrable function f over minus pi to pi. Later we will define this Fourier series for arbitrary function, not an arbitrary function, the Fourier series for integral function in arbitrary interval. Okay, and here we use this e power inx as the we use this functions e power inx to define this Fourier series. And later on we will generalize this e power inx with some orthonormal basis. So for the time being, we define the integrable Fourier series of integrable function over the interval minus pi to pi using e power inx. Then we if we define this Fourier series for an integral function, we are not aware of the convergence of this. Okay, what type of convergence can be discussed, that is a problem. So we will next we will define the Fourier series for arbitrary orthonormal for a function defined on arbitrary interval with some orthonormal basis. So we first define, after that we will discuss the convergence of this. Okay, so next we have definition 8.10. So this is the definition of orthonormal functions, orthonormal family of functions. Let summation phi n when n is equal to 1, 2, 3, etc. be a sequence of complex functions on AB. We replace this minus pi to pi by AB such that integral a to b phi n x phi m x conjugate dx equal to 0 for n not equal to m. Okay, so if in fact this integral is nothing but an inner product that we will discuss later. So if we define integral a to b, if we choose phi n such that integral a to b phi n x phi into phi m x conjugate dx equal to 0 for n not equal to m, then this system of functions or family of functions phi n is called orthogonal system of functions, okay, on AB. And in addition to this, if we replace this phi or in the case n is equal to m, or you replace this phi m by phi n itself, then this becomes integral a to b phi n x into phi n x conjugate, that will be phi n x mod phi n x squared dx. If this quantity is 1, then Apart from this, if you have this result, then we can say that the system phi n is orthonormal system of functions. Orthonormal is called, this is called orthonormal system of functions. Okay, so this is the a little bit generalization of Fourier series of a function with respect to the orthonormal basis phi n. Okay, if we replace this e of e power inx by this phi n, we can define Fourier series and Fourier coefficients of an integrable function. So for example, you can take this family e power inx is an orthonormal system of functions. For the verification, we have already discussed the integrals e power inx and e power minus imx will satisfy the condition that 0 when n equal to n not equal to m, and as n equal to m we have 1. So this satisfies the conditions for orthonormal system of functions. So we can get the e power inx as the orthonormal system. Then we can define for corresponding to any orthonormal system of functions, we can define Fourier series. Okay, if we define if we start with an integrable function, if f is integrable function on ab, we replace that minus pi to pi by ab, then we define Cm in using the fact that 1 by b minus a. So we write, sorry, this before that we Cn is equal to integral a to b f of t phi n of t conjugate dt. First you define this is called Fourier coefficients of f with respect to phi n, with respect to the orthonormal system of functions phi n. Okay, so using this Fourier coefficients, you can define summation, and this summation n equal to 1 to infinity Cn phi n x. Okay, if you define this series is called the Fourier series. Okay, this is called Fourier series of f relative to with respect to phi n. So corresponding to each orthonormal system of functions, you can define Fourier series for integrable functions over an interval ab using this fact. So later on we will discuss the convergence notion of this. Okay, in order to discuss the convergence notion, we need to get a distance. So in order to get a distance, we start with an inner product. Consequently, that induces a norm, and using that norm we can discuss the convergence notion. So in the later classes we will discuss what is the convergence, how or when they converge, when this Fourier series converges. Okay, so we write this f of x equivalent. Okay, so this symbol denotes the fact that this Cn's are obtained from this f of x using this formula. So that is the meaning of this statement. So if we write f of x, the Fourier series of f of x is this, that doesn't mean that this series converges to f of x. Okay, so the meaning of this is f of x, the coefficient of this Fourier series can be extracted using this f of x. That is the only meaning of this symbol. So later we will discuss how or when this Fourier series converges to f of x. Okay, so what will be the distance to take to get the convergence of this to f of x. Whenever this Fourier series, the right hand side, converges to f of x, then only we can write this f of x equal to summation n is equal to 1 to infinity Cn phi n x. Okay, as far as this is not convergent, we can write only this symbol f of x, the Fourier series of f of x is this one. Okay, this doesn't mean that this trigonometric series converges to f of x. Okay, the next classes we will discuss the convergence of this Fourier series, the notions of convergence of Fourier series to the corresponding f of x. Okay, thank you.